So now you are able to see my slides.
Yes, sir.
Okay. So basically, the slide says that you have a endurance limit available. You, as you're mentioning, 5 in 10 to the 8 is for the non-ferrous material. Okay. So one can still use 10 to the 6 for calculation, but you are increasing the stress level, right? It is asymptotically decreasing. Instead of 5 to 10 to the 8, you are taking at 10 to the 6 means stress level, which is not correct. Now, the factor that affects and which is quantifiable, one can find the knockdown factor is component size, type of loading, surface finish, temperature, reliability. Of course, other factors are there, but that's not quantifiable. It's all qualitative, which I will be covering. See, as I mentioned, this the experimental data they did for endurance one, it is 0.3 inch. Your endurance limit is 33, but when it go 20 times of your diameter 6.75, it is come down less than 50%, and close to 50% endurance limit is getting affected the size. So basically, large parts fail at lower stress than the smaller parts. The shining example is if you take a stick and with a finger, it's a long stick, you can break it so easily. But take half of that, you need little bit force. If one is small, it's difficult to break it. Forget about your so that is a smaller thing. It will become more difficult to break it, and this mainly due to the higher probability of flaws being present in why at larger thing is because if you take we are talking about smooth specimen, right? Is a round specimen cross section. If you give the bending, you know that this is the distribution of stress distribution, maximum at the top and what negative. But larger volume, the area will be subjected more stresses, and you will have always inherent defects like porosity and all. The number of thing will be more at the larger. That's why it is a very weak. They fail at the lesser number of cycles. Now we'll see the size factor. Okay, we are talking about size factor only, right? Yeah, this is a size. This is very generic, large or small. Now to get what is exactly factor, you need to have a empirical relation. So this is the test they have done with different diameter and specification in mm. You see a lot of scatter, but that is what industry follows. This is constant till 8 and beyond that it varies. But when it comes to size effect in AFI, it's different. Okay, there you are talking about whole E to power R divided some value to the power something is there. If you people who have used AFI, that is size, because the test they have done for half an inch, but your structure is having different structure. So how to correlate the test? So that's the size factor first. But here this is for domestic size factor. You are considering the size based on the diameter and the circular hole. Then for rotating, this is the empirical formula is obtained based on the test, and it has got both SI and IS unit. And anything which is more than 250 one has to use standard constant factor 0.6, 60%. Now the test has been done that Holler's one is solid, quarter inch, 6.25, mirror polish, and round. But some cases you might have a specimen which may be round but stationary, which may be annular, say pipe type also may not be solid. But how do correlate to take the effect of size effect? So if you people have used Csize, okay, it gives very good explanation of that, how to take 95% of some area, because that is whether it's a torsion or bending, you have a maximum bending stress occurs at the top 95% only. So it is equivalent to some what is called angular ring type of, not angular, it's a ring type. So there's a relation. This you have to take it for granted. This is not a granted, it's an engineering judgment. See, obviously area of 95% of thing, you know, pi d square by outside by thing, that is a equation used. Then you get a relation. The area corresponding to 95% of thing is coming out to be 0.076 is d square. D is the diameter of the actual specimen. So now it is equivalent to that 95% of d, and subsequently all equivalent d is calculated. even though your cross section is rectangular or square or anything, but you have to find out the equivalent. For this case, you have a non-rotating. It's a solid. Cross section is circular but non-rotating, but there is a size factor required. So in that case, that we saw the previous slide, some D is there, no? In that case, you have to use D equivalent, not that D is the actual size of the aircraft, part or component or test specimen. But when you calculate for a component, structure will have different cross section. I will give you nicely very good example down the line. So in that case, you have to find the D equivalent. And for rectangular, you have a 2 moment of inertia. Load can be applied about this direction, and based on that, again, it is given a D equivalent is, if you know the width and the height, square root of that 0.88 will give the equivalent size. Then sometimes cross section can be I section, C section. It's not I'm talking about the spar or things. Your structure bracket also can have a cross section like this. Any one of them. In that case, based on the width, direction or axis of rotation or moment of inertia load is acted, you can have a A95 equivalent equal to that. This is the example how to take care of size. So this is a bracket machined from the plate. It will have a 2 machine in the depth this side and the behind below that, the side view of that bracket, and you have a circle stress concentration factor here, and obviously one fillet also. Now we are considering the fillet. Okay, in this section you have a you want to calculate the fatigue life of that. So the material is known, you will have SN curve, but you have to consider how to take care of the size factor. You take a cross section, it looks like I here because it's a machine from both sides. It looks like SN. If load is acted not out of plane, it will be along this direction. Obviously, it will be about 2 axis. It will be operating. Accordingly, you have to find out what is the A95. Okay. And there are certain points to be considered. Those are very specific nature. There are certain points like though you are using that equation for the size factor, but there will be some differences between the ground realities and thing when you try to do prediction, correlation between the test and the analysis. Basically this effect will have a very long range in the terms of 10 to the power 5, 6, 7 that way, not in the beginning 10 to the power 3 or 10 to the power 4. The effect of small in diameter is up to 2 inch. Even in bending or torsion, there is no effect. And due to the processing problems inherent in large component, there is a greater size. Though you might have known the diameter of that big thing, if you use that formula, there is but actually the reality there will be some additional. It will be more because there are things may induce